All right, in this second block of review questions, we're going to continue our look at quadratic equations for one more example. In the last one, it was graphs to equations. This one, we have the equation, and we're going to pull out the data. And particularly, we're going to do it in a word problem application. So the value of Jennifer's stock market portfolio is given by this function, v of t. So whatever's happening in this stock market account, it seems to be following this mathematical model of the equation. V is the value in hundreds of dollars, and T is the value in months. How much money did Jennifer start with? Now, typically, we start with our functions, ax squared plus bx plus c. We put them in order. And something significant happens with the value of c. That is the y-intercept point. And in application, that would be the starting amount. And since this quadratic equation is in reversed order, the answer to A is that the y-intercept point is 0, 50. And that means that that's 50 100s. So that's $5,000 to start. Second question here is, when will the value of Jennifer's portfolio be maximum? Now, one thing it's nice to remember here is that we are looking at a quadratic. And also, because it is in reverse order, the A number is -3. And that's forcing my quadratic equation to, here's 50 where it starts, and it's forcing it to go up and then curve down. Now you can't get any, I suppose the portfolio could go in debt somehow if it's leveraged, but I won't make it that way. I'm just going to stop at that. Okay, so it does have a max. So there's two questions here, the time and the value. And the time is this number right here. We need to find that number. So all of this is related to the vertex point. And hopefully remembering to find the vertex, there's a little formula for it. The coordinate of the x-coordinate, is -b over 2a. And so in this case, that'll be negative of b. My b number is 73. Divided by 2 times -3. Now, when we run that in the calculator, it's about 12.16, I think. And let's just call it 12 months. So, after 12 months, her stock investment reached its highest point. And how much was that highest point? That's the C question. Well, that would be, in this case, I used X and Y, but this graph has no X and Y. It has T's and V's. So the value of her account would happen about at 12. So I'm using the round off number, and so we have to just plug that in. So we're going to go 50 plus 73 minus 3 times, and just for emphasis here, I'm kind of using this as my input, 12 months, 12 months, and 12 months. And then we have to run that in the calculator. And when we do, it's, because we put in an approximate value, it's 492. And that is in 100s of dollars. So the max value was equal to $49,200. So her account did really well in those 12 months. Okay, so we've answered the question here by understanding things like the vertex. However, to extend this problem, any equation that's quadratic, there's many things that I want you to be able to tell me about it. I want you to be able to tell me additional questions or additional information here. Like, what is the y-intercept points? Any quadratic, I want you to be able to do that. Now that's easy. We already figured that out. I would like you to be able to find B, C, D, E, X intercept points. And that is question mark, that's when y equals 0. So in order to solve that, we're going to have to solve an equation. 0 equals 50 plus 73t minus 3t squared. And that's an equation that you would need to solve for this thing. And so there's a couple of ways. You could try to factor it, or you could try the quadratic formula. But I'm going to come back to that in a moment. I want to hit all the bases here about things that I would want you to be able to tell me about any quadratic equation. Another thing here, which is kind of easy, is tell me the axis of symmetry equation. And because we already have the vertex, well, no, let me ask for the vertex first. That's something that I would want you to be able to find. And we've already calculated the vertex kind of in parts here, but we found it was 12 and 492. Next, I'd like you to be able to tell me the axis of symmetry equation, which is cutting through the vertex right here, and that happens when x is 12. So x equals 12 is that axis of symmetry equation. These are all characteristics of quadratic equations that I would like you to be able to identify for me and understand those well. Now we have one thing that's not done yet, and that is the intercepts. That's going to take a little bit of work. So you have a choice here for the quadratic. To find the zeros, you can use the quadratic formula or factor. And if it turns out, you can try the formula. You should maybe test yourself on the formula. But it turns out this does factor. We will have 0 equals, and we need minus 3t times t. I'm not sure if it's minus or plus yet. And 50, if we go 3 times 25 and 2, that gives me 50, and I need a positive and a minus, and that turns out to be a correct factoring. You can check on your own here if you like, but I've got two solutions that I'm looking for now. 0 equals 2 plus 3t, or 25 minus t equals 0. Now if I add t, I get here t equals 25. If I solve this one by minusing the 2 and going all the way through, I'm going to skip some steps here. I get t equals negative 2/3. Now the quadratic equation has two answers. I've got zeros at 25, and I have another 0 over here at negative 2/3. Now remember, the horizontal axis represents time. So negative 2/3 months before the investment happened doesn't make sense in the word problem. It is a 0 for the quadratic equation, but it's not a solution in this physical application, so we can throw that solution out in this context. But definitely there is a 0 at 25. So what happens in 25 months? Well, the value goes down to 0. So if she waits that long with this particular model, she's going to lose all of her money. There is kind of a quick example. You might try thinking through this on your own without looking at this and be able to pull out all those details from a quadratic equation. All right, the next thing I want to transition to here is looking at polynomial functions. It's a natural step beyond the quadratic function, and there's several things that we should review. Just some quick reminders. There's something called the power function. Y equals x squared is the power function. Y equals x to the even is a power function. They're single terms. Could be 4th power, 6th power, and in fact they also have coefficients that can stretch them. But in every case, depending on a, these power functions will go up or maybe down depending on a. So the important thing to notice here is the end behavior. The tails are both up or they're both down. And we're going to use that to help us graph. So in this case, both tails are going up. But we also have power functions that are odd, like y equals ax to the cube power, y equals ax to any odd power. And when we graph those, we get a certain characteristic shape. We call these the U shape. And these have a shape that we were referring to as a chair shape. You know, it's not a very comfortable looking chair, but it's kind of a shape depending on how extreme these turns are. And so the key feature of the odd power functions is the end behavior. It's always opposites. One goes down and then the other goes up, or one is up and the other goes down. So you have these end behaviors, and we're going to need that end behavior to help us graph. So that leads me into polynomial functions. If we have a polynomial function, p of x, it's going to have a leading degree. It's going to have a x to the n power plus bx to the next one down, possibly n minus 1. And this polynomial is going to be going, have more and more terms. Eventually I'll have, the constant plus c. So some examples of this. The polynomial function might look like minus 2 x to the 5th power plus 4x squared minus 7. Now, the reason this study about the power functions is important is because for every polynomial, the degree of the leader when x goes to infinity will have the same end behavior as power functions. So this 5th power will eventually take over and determine the outcome of the tails. Now, one of the things I didn't make a big deal about here, but this chair gets flipped if a is negative. And in this case, we have negative 2x to the 5th as the leader. So it's odd, so the end behaviors are going to be one up, one down. And the positive one starts down and goes up. But the negative one, we know, is going to start with one tail going up, and then the finished tail is going to be going down. We know the end behavior of this polynomial. because this power function is the lead term of this polynomial function, and as x gets really large, this is all that's going to matter. So now when we start to sketch this polynomial function, we know something about its tails. Okay, next thing I want to review about polynomial functions is the relationship between the polynomial function and its linear factor. So any linear factor of p of x in the form x minus r is an indicator of a, quote, I'm just going to say nice. Formally, I should say a rational zero. Or you might say an indicator of the x-intercept point. So let's say that we can take a polynomial and factor it, p of x, and we get it down factored to 6 times x minus 3 times x plus 2 times x plus 1. These are linear factors, so I have 3 linear factors in here. Now, what does this have to do with the zeros? What does this have to do with the x-intercept points? Well, solve it. If we solve this for 0, we can solve for x. So what we're doing here is we're saying y equals 0. What's the x number? Question mark. So if y equals 0, I can solve this and find x values. And that means x minus 3 would have to equal 0, just like quadratic equations. And so each of these linear factors is solvable for 0, so I get an x equals 3 is one of the zeros. Minus 2, minus 1. So there's a 0, and a 0. So these are all x-intercept points. So I can call them zeros, or I can call them x-intercept points if I write 3, 0. Because when x is 3, y is 0. Negative 2, 0. When x is negative 1, y is 0. So zeros and x-intercept points are very related ideas here. Now, what is the big deal about that? That is also helpful for graphing. If we know the tails of a polynomial function and we know where it crosses the x-axis, we've got some solid clues for how to graph. Now, I have one more review topic related to the zeros here. And so that is called multiplicity. Of the zeros. So the multiplicity of the zero is based on the degree of the factor. So if my polynomial, for example, was negative 7 x plus 2 to the 4th power times x minus 1 times x minus 6 cubed. So if I were to solve this, minus 2 would be 0. X equals negative 2, but it also has a multiplicity. equal to 4. So this factor, x plus 2, got used 4 times in this polynomial. X plus 2 times x plus 2 times x plus 2. If we solve this one, x minus 1 equals 0, we would have a 0 at 1. And it has a, that's unfortunate. I'm going to change the problem. Let's say that is a different number. Let's call it 5. Well, x equals 5. Now, how many factors of x minus 5 are there? There's only one. And then lastly, x equals 6. That has a multiplicity equal to 3. Now, this also helps us know about graphing. When you have repeated factors, you get different outcomes with graphs. So there's 3 possible scenarios with your zeros when you graph zeros. If you have a 0 here, I'm just going to put a random graph, and the polynomial is graphing something like this. The tail comes down, it hits the 0, and it comes out. Versus this graph here, here's the tail, hits the 0, bounces and comes back down. Versus this graph here, where the 0 comes up to it, it looks like it's going to bounce. It's curving in, it looks like it's going to bounce, but it doesn't, it curves out. So it kind of slowly comes in and slowly goes out. So we have 3 different kinds of 0 intersections on the x-axis. For lack of a better way to describe this, I just say straight through. This one is bounce. And this one, we refer to it as a chair. It's kind of like a chair. Now, these zeros happen in graphs when the 0 is, the linear factor is degree 1. Or we could say multiplicity 1. And the bounces always occur when it equals degree even. 2, 4, 6, 8, 10, even. And the chair always happens when the degree or multiplicity equals an odd bigger than 1. So 3, 5, 7, 9. So with these 3 characteristics, the multiplicity of the 0, being able to find the zeros from the factored form, and knowing the end behavior, we can make some pretty good sketches of our polynomial functions. So, when we're working with polynomial functions, it's quite helpful to find them. Oops, we're not worried about the 0 anymore, but the polynomial function, it's best if we can get them in its factored form. Let's look at a few examples. All right, let's sketch a graph. Now the one I have here, this polynomial function, is really pretty complicated, probably way more complicated than you will see. But if you can see all the process in this one, then you can do the easier ones. So we need a couple things out of this. We need to know the end behavior. And the end behavior comes from the leading term. So the leading term has, it's not in its standard polynomial form. It's broken up into factors. So if we're going to figure out the end behavior, we got to identify the leader. Now, this part of it has a leader of x cubed. This second factor has a leader of x squared. And all of it is multiplied by -2. So if we were to distribute and multiply this whole thing out, we would find all the terms, but we don't need all the terms. We just need the leader, which is -2x to the 5th power. I did that by taking the leader of this one, the x squared times the x cubed. That made x to the 5th and times -2. Now, because it's odd and a equals a negative, I know the end behavior. The tails are going to start from the top and come down and end. So at the left side it's going up to infinity, and on the right side the y's are going down to infinity. So I have a solid clue now to help me graph this. I've got my tails. Next thing I'd like to know is my zeros. And the only way to get the zeros is to factor. So let's factor this. P of x, -2. So the first factor is a difference of squares. That's easy. The next one, there's a GCF in here, x. And when I take that out, I'm going to have x squared plus 4x plus 4. Now that one's not completely factored yet. So when I finish off factoring, this one will be x plus 2 times x plus 2, which I'm going to write as a second power. Okay, so I have all my zeros. Well, I haven't identified them yet, but the zeros are x is going to equal -5 and +5 and 0 right here, and then -2 right here. But I want to take a note here. This one is multiplicity equals 2. That's even. That's going to change how this graphs a little bit here. Okay, so we know the zeros and we know the multiplicity. I'll make a separate. Let's do it this way. So there's my 4 zeros, 1, 2, 3, 4. One of them got repeated. So this one is multiplicity 2, that's multiplicity 1, 1, and 1. So some of the zeros, when we graph them, are going to go straight through, and this one is going to have a bounce. All right, let's get to sketching here. Now, on the x-axis, we have a pretty clear view of all of the x-axis values. We really don't need to go any bigger than -5 and +5. 1, 2, 3, 4, -5, -6 just for cushion on the edge, 1 on the edge, 2, 3, 4, 5, and 6. So what all these factors tell me is we have a 0. Now, I don't know anything about the y-axis yet, but I do know a lot about the x-axis. So, for my graph, let's make it in purple. I have a 0 right here. At 5, I have a 0. At 0, it's going to cross right at the origin, and at -2, I have a 0. So the function is going to hit these points. Now, I also know the tails. The left side tail is headed upwards, And the far right side tail, as x goes to infinity, is headed downwards. So now I need to connect the tails to the zeros. But as I connect the tails to the zeros, I have to take into account what the multiplicity is doing. So this 0 here at -5 is multiplicity 1. So I'm going to come straight through it. So the graph is going to come down straight through that. At -2, though, it's not going to, it's going to bounce. So I'm already below. I don't know how it's going to have to turn, but then it's going to have to bounce. Okay, now at 0, it's going to have to turn, and then it's going to have to go straight through at 0. And then it's going to have to turn again, come down, and come straight through the 5, and then connect to the tail. So, the only thing that remains is how specific I want my sketch. And this is -2, 0, and 5. So, there's some valleys here and a peak here, and we don't know about those valleys and peaks. And so it depends on how detailed we need to have our sketch. But for my purposes, this would be a reasonable sketch. I kind of left it dashed because we might need to fill in some details here. And if we wanted to, we could plug in a x number in between. So if we plugged in an x between -2 and -5, like -3 or -4, I'd plug in a whole number. I don't want to do decimals and plug decimals into that crazy thing. But if we did plug in a number, it would give us an approximate value. Now we're not going to know exactly where the peak or valley is. So I'm not going to detail it any more than this. I'm not going to worry about these peaks. So on my y-axis, if I plugged in like 2.5, that's halfway between 0 and 5. That might give me, it's not a guarantee that's the peak, but it'll tell me some target I can shoot for. And the same with -1 and say -3 or -4. That would give me a value to kind of to have a target to drop down to. But I'm not going to detail that out. So for sketching purposes, remember, we're not drawing a perfect graph here. We're just sketching. So I'm going to say it does something like this. It bounces straight through, comes up, straight through, and now I have a reasonable sketch of my graph. So, oops, I forgot to connect this tail. There we go. So we've got a reasonable sketch. We don't have the peaks and valleys detailed out, but we have an idea of what this polynomial graph is going to look like. And if you wanted to be more specific, you could plug this into Desmos and see, and I happen to have it over here for you. So when we do it in Desmos, the scale turns out to be extremely high. The peaks here, the peak here, or the valley here is at -4.2, and it's at 300. And this has a valley here at -60, and this has a peak here way up at 2,700. So we might not have been able to get those targets too well without doing a lot more calculations. But you can see the basic tails and the zeros. We have a reasonably close looking sketch. So that is the power of finding the end behavior and the zeros to help us sketch. Okay, now I got another one for you. This time we're going the other way. I've given you a graph of a polynomial function, and we want to write the equation. So writing the equation, we've got a couple of clues here. So notice the tails. They're both down. This only happens when the lead coefficient is a power function that's even. So we have an even leader. So we got one clue there. Another clue is zeros. We have a 0 here, a 0 here, and a 0 here. So each 0 corresponds to a linear factor. X minus -4 has to be a linear factor. X minus 0 has to be a linear factor. And x minus 1 has to be a linear factor. Now this one up here, x minus -4, I can just say is +4. So all of those linear factors have to be part of the polynomial. Now there is one other issue here. It's the a coefficient. The tails are down, so it's got to be negative. But we don't know what it is. Is it a big number, small number? We don't know. We're going to have to do some algebra to find out. So, but we have the makings of our polynomial. Now the linear factor, I should have said this one too. This is kind of, it's a redundancy. I don't need to write x minus 0 for this 0 here in the origin. I'm just going to simplify it as x. That's my factor. So the polynomial, don't forget, it has a. We haven't figured out a yet. But it is going to have x plus 4. It's going to have x, and it's going to have x minus 1. Now the next thing we have to figure out is the multiplicity of these zeros. So at the -4, what kind of behavior are we seeing here? Well, this is the chair. It looks like it's going to bounce, but it doesn't bounce. It touches and crosses through. That's the chair kind of behavior. This has to be multiplicity odd. Now, when we hit the 0, that was hit 0 and bounced up. That has to be multiplicity even. And then this last 0, did it bounce? Did it kind of slide in and slide out? No, that's straight through. That is 1, a multiplicity 1. Now, we need to make those observations so that we can put the proper power on the polynomial linear factors. So at the x minus 1, that is a straight through 0. That's a first degree 0. At x equals 0, I'm sorry, at x minus 0, or just x, that's an even one. Now we could do 2, 4, 6, 8, 10, anything even. But we might as well keep our polynomial as simple as possible. So let's use the smallest even that we can come up with. And the same is true with x plus 4. That one has to be odd, like 3, 5, 7, 9. Let's use the smallest possible power that we can come up with just to keep our polynomial as simple as possible. So we had to account for the degree of all of our linear factors. The polynomial is almost done. There is only one last thing to figure out. How are we going to find a? Well, typically when we're after a, the only thing to do is plug in a point. Now we've already used the zeros. We need a new point, something that we haven't used before. And I'm sorry the graph doesn't communicate that well. It should be communicated really well that you have a specific point in mind. And I am going to decide that for us right now and just call it this point here is -2, 100. Okay, so now we're going to use that specific point on the graph. That's not one of our zeros. It's a new point. We're just going to plug in. So we got tons of math to do here now. So 100 equals a times, I'm plugging -2 in plus 4. That gets cubed. Now I'm going to plug in -2. That gets squared. Now I'm going to plug in -2 minus 1, which is, well, I'll simplify in a second. So 100 equals a. -2 plus 4 is 2 cubed, which is 8. -2 squared, which is 4. And -2 minus 1 is -3. And now we need to simplify that a little bit more. 8 times 4 times -3. I'm doing that on my calculator, and I get -96. And if I divide by -96 on both sides, I get an A number. Not a very nice number, but it is negative. And that corresponds to what we thought. The negative means the U, so the leader is even. Well, let's go back and talk about that in a second. Let me write the polynomial. P of x equals -100 over 96 times x plus 4 cubed times x squared times x minus 1. That is the polynomial that makes the graph that we were looking at. And just kind of double checking this whole thing. This one is a liter of x cubed. That one is its own liter, x squared. And this one is linear, so it's x. And if we multiply all of these x's together, we get x to the 6th power. There's the even liter. But it's multiplied by this negative, which means the U-shaped tails are going down, just like we see in our picture. So I'm just trying to connect the relationships here, but we've solved for a pretty challenging equation based on knowing just a couple things about polynomials, their zeros, their multiplicity, and their tails. All right, look for more of these to study. I definitely am putting one of these on the final. All right, we're going to change gears again and look at now a short study on exponentials and logs. Mostly logs, but I want to review these with you just to get your mind back into the idea of these two functions. So first, we saw log exponentials. Say, for example, we're doing b to the w equals r. Well, it's possible to rewrite this. A log function is the inverse of an exponential. So we can rewrite this as log. The base is b, but the r is now the input, and the w is now the output. And one thing to remember about logs is the log answer is always an exponent. W is the exponent, and that's exactly where we got it from. And vice versa, we can take a log, say it's base a of p equals q, and that can be rewritten as an exponential. Now it's log base a, so my exponential has to be base a. And here is my log answer. Well, log answers are always the exponent. So I'm going to put it as the exponent on a, and that's got to equal p. So here's just some practice with rewriting between logs and exponentials. Now we need this because some exponential equations or some log equations can be solved if we rewrite them into their inverse functions. A couple of other reminders. Log base 10 of x has a nickname. We just call it log of x. That's the common log. And log base e of x also has a nickname, ln, or natural log. So those are some shortcut formulas we used. Log base b of 0, can't do it, it's an error. Log base b of a negative, can't do it, it's a negative, as an error. Putting a negative or 0 in a log is not in the domain, and it's going to give you a domain error. Log base b, though, of 1 equals 0. That's doable. Another property, these are log properties now. Log base b of b equals 1. Now, here's another log property that we learned. This problem is log base b, and the inside is exponential base b. So an exponential base b and a log base b, these two functions are inverses of each other. They're going to cancel each other out, and we get m. Here is a similar property to this one, but not exactly the same. Log base b of x to the m power. Now this is exponential base, I said that wrong. This is log base b, and this is exponential base x. Exponential base x cannot be undone by log base b. But there is a property similar to this one where it turns out we can pull the exponent m out as a coefficient. So this is quite handy to simplify more complicated log properties when we use this principle here. There's two more that I want to remind you of. Log base b of a product m times n. And that we can say is log base b of m plus another log. If you have multiplication inside, it's a log plus a log. And if you have subtraction, a log minus a log, it's a division inside. I'm not going to write that one down. Let's do some solving here. Let's solve log of 10 to the 5x plus 1 power minus 6 equals negative 4. So I need x by itself. Well, subtracting 6 isn't going to help me with the log at all, so let's get rid of the 6. Easy to get rid of. Now the log is isolated, and it equals 2. Okay, hey wait, this is exponential base 10 and this is log. Right up here we saw that log base 10 is the same as log, so this is log base 10 and exponential base 10. That is exactly this property here. Exponential base 10, log base 10, they're going to cancel out. The only thing left is the exponent. Easy. Minus 1. So 5x equals negative 1. X equals negative. It does not equal negative 1. It equals positive 1/5. All right, there we solved. Let's try another solution, and a more hard equation here. Probably the hardest you might possibly see. We're going to take log of x minus 2 plus log of x plus 1, and it's going to equal 3. All right. Well, I cannot get x by itself because x is stuck inside a log function. In fact, it's stuck inside of two different log functions. Can't get anywhere here until I at least have only one log function. Well, fortunately, I have this rule up here that says a log plus a log can be rewritten as one log with a multiplication inside. So I'm going to use this law here to compress these two things into one log. Alrighty, so I have a log statement here. I'm trying to figure out how to get this x by itself. Well, x by itself is stuck inside of a log. I cannot get at the x answers until I get it out of the log. But I could rewrite this. I could flip this inside out, change the log problem into an exponential problem. And that might help me free out those x's. So this is log base 10. I'm going to change colors to do this because now I'm doing the inverse. It's log base 10. So when I flip it, it's exponential base 10. What is the 3? The answer to a log is a power. This is 10 cubed equals what was the input before in the log is now the output of the exponential. All right, so sure enough, now I've got an equation that's a little easier looking to solve. We got some work to do though. Let's get rid of parentheses. That's 1,000, 10 times 10 times 10. I have to FOIL this, x squared minus x minus 2. And now I'm going to have to minus 1,000 on both sides to get it equal to 0. Because we wound up with a quadratic equation. We're going to have to solve it as a quadratic. And so at this stage, we might want to try factoring for a little bit. But to come up with two numbers that multiply to 1,002 and subtract to 1 doesn't seem likely. So I don't think it's going to be worth our time to try to factor. You could. If you found the numbers, it would be pretty fast and easy. But let's solve it with the quadratic formula. A equals 1, B equals -1, C equals -1,002. So x equals -b, which is 1, plus or minus the square root of b squared, which is 1, minus 4 times a times c, all divided by 2 times a. And so x equals 1 plus or minus. Let's get this calculation figured out. Okay, so you can see I filled it in. That's going to be 4,008 positive plus 1 more is 4,009. And then we're going to have to do the rest of that with the calculator. And you can see I already got those values here. I got two numbers. 32 point, let's round it off to 1 decimal. 32.2 or -31.2. And we were able to solve this equation. Everything good? All right, no, not everything is good. Remember the domain. Logs of negatives, impossible. Negative numbers are not in the domains of logs. Log of 0, no good. What happens if I plug this answer in here? negative 31. So negative 31 minus 2 will be negative 33. I cannot do a log with a negative input here. So this quadratic solution, it works for the quadratic equation, but it does not work for the log. This is an extraneous solution. We're going to have to throw that one away, and we're only going to keep the one solution here. 32 is going to be fine, because 32 minus 2 is 30, and 32 plus 1 is 33. So those logs are going to work out great, and we could check them to see. But here we've solved that's a really hard log equation. So if you can see how that works and study it out, most of what you will encounter won't be that hard on the final. All right, I've got two more things related to, in this case, exponentials, a couple models. Here's a population of Costa Rica, and in 2013, it was 4.872 million people. And its growth rate was 1.27%. So let's come up with a mathematical model here. And so I think P of t makes more sense for population. So let's define P of t equaling to the population. But we're going to count people by millions of people. And t equals years. But not years from 0 from when Jesus was born, but years after 2013. And we need a model. Now our population model, we're going to use a b to the t power. And what's happening with the a number? Well, the a is our starting value. So at 2013, t equals 0, and the population is 4.872. So this is our start value, and that equals a. So we'll take 4.872 times... All right, sorry, I interrupted myself and I forgot where I left off, but I can see we have to find b. How do we find b? Well, b is the multiplier. And so b comes from the percentage that we're multiplying. Now, when the population grows, we're assuming that we keep 100% of the population, plus we're going to grow 1.27%. So when we take from 1 year the 100% population plus an increase on that population, it's like we're taking 1, which is the decimal for 100%, plus 0.0127, which is the decimal for 1.27. And so b, our multiplier, is 1.0127. This whole logic here is how we got our little formula for b, 1 plus r. And so that's how we can find our multiplier. So in this problem, it is 1.0127 to the t power. So we just created a mathematical model here for Costa Rica's population. That was part A. Part B, the year 2030. Well, in the year 2030, that is 17 for t, because 2030 is 17 years after 2013. So we're going to have to plug that in and do P of 17, and we'll let the calculator take care of that step. So 4.872 times 1 to the 1.0127 raised to the 17 power, and we get 6. Oops, I didn't remember the number. 6.037. Let's just round that off, call it 6. Well, no, we're talking about millions of people. That's a lot to round off. 6.037. 6.037 million people. So there is our solution to the second part of this problem. All right, I got one more of these applications for you. Okay, one more example. Fluorine 21 has a half-life of approximately 5 seconds. The experiment started out with 25 milligrams of fluorine 21. How much is left in 1 minute? Okay, there's a question there, but there's a more important question. Which exponential model is best? The incremental model or the continuous model? So let me define I'm going to define variables for us first. So we're going to have t in seconds. And we're going to have q, the quantity or the amount of the F21 in milligrams. Okay, now when we talk in terms of models, we could say q equals ab to the t power. Or we could say q equals a e to the RT power. This one's continuous, and this one is the incremental. And if we're thinking about radioactive decay of a substance, that's not like a bank account. Excuse me. A bank account, pays once a month or once a year or once a day. But the radioactive decay of this chemical is going to be a continuous interaction, a continuous chemical reaction going on here. So really, the continuous model is our best choice. So technically we can get away with the incremental one, but if we're looking for the best model, let's go with the continuous model. So we have q equals a e to the RT. Now we do not know a and we do not know r yet, so we're going to have to figure out our model. But fortunately, we do have a few clues because the experiment started with 25 milligrams. So right there's my A number. And half-life. So in 5 seconds, we're down to 12.5 milligrams. So that gives us a point to plug in. So let's see if we can start doing some calculations here. First thing, I already know part of my model. A is 25. So I took care of that, step 1. Now step 2, I'm going to plug in this value because that's going to help me find my R. I do not know the decay rate. Now because it is decay, it's a half-life, so it's going down. The R is going to have to be negative. That's my only clue here. So this is my second step. Plugging in 12.5 equals 25 e to the RT. Divide 25 on both sides. So that's a half. We're left with half of the quantity. Now I gotta, oops, I forgot. I plugged in the 25, but I forgot to plug in 5 seconds. So I have 5 seconds here, and I have 12.5 milligrams here. Okay, so we can start solving now. Oops, need that 5. Somehow I have to get R by itself. Well, we could use the natural log, so we could flip this equation inside out and rewrite it as a natural log. Yes, I'll rewrite it. So it is going to be natural log of 1/2 equals the exponent 5r. That's easy to solve. 5's cancel, so r equals natural log of 1/2 divided by 5, and we're going to get a decimal for this here. So it was natural log of 1/2 divided by 5, and I get this negative decimal here, which is a decay rate of 13%, almost 14%. So let's not, I'm going to round it off to 0.13863. 1386.3. Okay, so that means our model is finished. We found the model Q equals 25 e to the negative 0.13863 times t. That's the mathematical model for this fluorine 21. But we do have a question to answer. So that is our second thing here. How much is left in 1 minute? So let me call that part 3. No, yeah, part 3. Time equals 60 seconds. That means I have to solve for Q of 60. And now it's just a ton of calculator work. So if we go 25 times e raised to the, oh, I need that number there. I'm going to put that in, and I'm timesing it by, not plus, I'm timesing that number by 60 seconds for 1 minute. And that will give me about, oops, I touched the screen, it went away. 0.006, okay. 0.006 milligrams. All right, this thing has a fast decay rate. In 5 seconds, half of it's gone. In 60 seconds, it's almost all gone. The decay of the fluorine 21 is just about virtually used up the entire mass of the fluorine 21. Anyways, so I hope that was helpful. This review today that we did in class was focused primarily on stuff from our past with the algebra. Hopefully the trig material is still fresher in your mind, but you've got something here to kickstart your studies. I encourage you to do a lot of the practice worksheets. I encourage you to do the Newton optional practice tests for each chapter. The more you practice, the more problems you do, the better you'll be prepared. Also, if you have questions, there'll be ways for you to contact me in Zoom for one-on-one tutoring. Plus, we are having a review session next week on Finals Week. And all of that will be explained and posted in Canvas. Okay, study hard. Take care.